opinion. I'd like to introduce to you the next speaker, that's Jeremy Provost. And he is Heat Transfer Department Manager at Technip. And Technip is a large engineering construction company with over 30,000 employees. Technip is also working on the future of the energy industry, and one of the developments is ocean thermal energy conversion. Jeremy will introduce to us the development of the scale-up via 5 megawatt to 100 megawatt plant and the design of this plant. So please have the floor.
Yes, good morning, everybody. I'm very pleased to be there to present what Technip is doing in OTEC technology. So first, I will start with some slides related to Technip company, and the first one is related to HSE, Health and Safety and Environment, which is a clear involvement of the company, a commitment for that. And in my particular area of heat transfer, we are involved with quite a lot of oil and gas projects, and we have to perform some testing, and testing with hydrocarbon is not so easy, and you have to take care of safety, mainly of your installation. Here you have an example of a unit on propane that we developed with some partners, for which we apply a full and rigorous philosophy about safety. Technip in figures, it's a company which is 32,000 people about in 45 countries. We are involved in subsea, offshore and offshore activities, and we are mainly dealing with engineering, procurement and construction. And I would say I am the oil and gas guy here today for this activity. Yeah. So this is why I vote B at the last one. And so, yes, we have in 2015 about an adjusted revenue of about 12 billion of euro. Technip in offshore and subsea, it's developing and reinforcing positions through several alliances. Here you have some example with IRIMA for ultra deep water, Genesis with RPS Group, Serimax, Valore Group for pipeline welding, and you see Forces Subsea, which is an exclusive alliance with FMC. As you may know, next year, if all regulation organization validates this proposal, Technip and FMC will merge to be only one company. Over the last 5 years, investment in R&D was quite sustained, with 83 million invested in R&D in 2015. You see here some example for subsea technologies. What I want to point out in this slide is the two bottom technologies on the right side, the dual enhanced tube and the dual enhanced heat transfer tube for air coolers, which are our products that we developed with partners, Wieland and Kelvion, and which is really our product, successful product. Okay, suspense. Oops. Yeah, just here you have our portfolio. So this is the platform, floating or fixed platform that we use to design and manufacture. And also what is important, we are managing the transport and the installation of those platforms worldwide. And you can see at the top of the left side, the floating LNG, which we are very proud of. And we have the two in construction or in commissioning right now. This is the Shell Prelude and the Petronas Satu floating LNG. So now switching more on what we are here today about OTEC. For us, we have three main technology challenges. For this OTEC, we have the risers, and this is something that we already designed and studied for our floating LNG. We have the rotating equipment, the pump and the turbines. And for that, last year, my colleague James Bryan presented a paper at the third OTEC Symposium, and you have the heat exchangers. About heat exchangers, here you have quite a nice picture for us. This is a seawater gas cooler that we installed in Middle East. This one is equipped with a titanium low-fin tube and is working quite well. This is a gas cooler. We have a very long and huge condenser, also equipped with a titanium tube for seawater cooling. Why heat exchangers are so important? In fact, they are about almost half of the total investment that has to be done for the OTEC project. And the second is the risers. What we did, we evaluated for a 5 megawatt and a 100 megawatt net power the three technologies on the key parameters listed here. We have the total weight, with each quite important for offshore definition, the number of items, which will control the piping and manifolding, the cost itself of the technology, the volumetric heat transfer coefficient, and I talk about volumetric in order to take into account the improvement in the heat transfer coefficient as well as the densification of the heat transfer area within the equipment that you want to maximize. On the other side, you have the falling sensitivity of your technology, and this you want to minimize, and generally it can work in the opposite direction with the maximization of the heat transfer coefficient. And what is also very important for all offshore projects is the technology maturity. The study we did is in fact based on something typical that you already well know. This is a typical ranking cycle based on ammonia with seawater, hot seawater taken at 26 degrees Celsius and cold seawater taken at 4.5 degrees Celsius. We studied first three, let's say, typical and approved technologies, which are shell and tubes, plate and frame, and brazed heat exchangers. And we have to take care about corrosion, fouling, and biofouling. If we play to the game of pros and cons for each technology, here what we have today with shell and tube heat exchanger is a very easy seawater side cleaning thanks to openable heads. You can have a limited number of items. If they are not very efficient, you can make them very big. And we are quite common to do it up to 20 meter long and 4 meter diameter. This technology is very common and widely used by offshore industry. We install them for our platform quite frequently. And so you have a very good robustness for a 20-year operation, which is a key parameter because you don't want to intervene too much on your offshore installation. As cons, you have higher ammonia inventory compared to other heat transfer technology, and you have also a lower volumetric heat transfer coefficient. If we switch to plate heat exchanger, what is interesting is to have the low cost of this exchanger itself. The fact that if you consider a semi-welded heat exchanger, you can open the seawater side and clean it. And also, this is something that in offshore industry is quite widely used, in fact, and well accepted. The point is the numerous items that you have with this technology limited by the volume of flow rate you can have in this equipment. It makes the piping complex and costly. And also for Technip, it's also the fact to have two-phase flow with this technology, which is we have limited reference with that, and this is something that we have to investigate more. Here, this is just to explain what is manifolding issue. This is, you see, 15 plate heat exchangers, gasketed one in that case for a seawater cooling water installed in Middle East. And here it's just to explain how it can be complicated just to install piping and manifold on this project. You see that on onshore plant in Middle East. We have the same thing in the hull of our floating LNGs. And to install that, this capacity, it's about 1 gigawatt installed inside the hull of a floating vessel is very, very challenging. The last one, the brazed heat exchanger. What is very good for this one is a high aluminum thermal conductivity, the high volumetric heat transfer coefficient compared to other technologies. This is a technology we know well for cryogenic application in olefins and in LNG. The good thing also is that you can clearly work at very low temperature approach, 1 degree and even less. Point is, as you have quite a limited channels, very small channels between the fins, you have fouling and biofouling sensitiveness that is quite important, and cleaning and maintenance is a key topic also. Here we summarize on this graph a comparison between the technologies around the 6 factors I presented before. 5, I would say, is the best note I can give, and 1 is the lowest for the moment. So here you see how we compare. Higher is the area of one color, better is not, I would say. And it's not so obvious to get a clear winner of this. We have on one side some approved and proven technologies such as the shell and tube, and you have on the other the quite performing well technology as the PFHE. And here this is the same thing for the condensers. But what is clear is to go to 100 megawatt net power, improvement in the technologies are needed. So these are some paths, some proposals that we are looking at. They are not all listed there, but it gives an idea of what we can look at. First, as an example, it's to improve the shell and tube. This is something we are working on now for 20 years with a partner, which is Wieland. We developed for our business 2 beautiful solutions. And I will talk mainly about the one dedicated to evaporation, for which this is a tube that is called GEWA PB, and it is shown on the left side of the slide. This one is working in improving the nucleation on the tube itself. Yeah. This is what we succeeded to do with Wieland. This is to develop and improve, in fact, nucleation and boiling at very low heat flux. Here you have the comparison between a plain tube with only convective boiling and nucleation that is promoted thanks to this thinning outside of the tube. And the picture on the right side is an exchanger that was the first reference using this technology, and now this is a leading technology on our market. Another possibilities, it is what we call plate and tube technology, such as the Z-Pack that is manufactured by Alfa Laval and Zimex. Cross-flow heat exchanger, quite interesting because of the tube itself side for the seawater, and the condensing on the plate side. It's of value because this is a very low pressure drop on the ammonia side. That is very interesting. This is a proven technology for the vacuum application in onshore petrochemicals industry, but need to be evaluated for an offshore topic. The last proposal, but on that I present today, is a new plate fin heat exchanger. There is a nice development made by French company, Fifth Cryo. They are now proposing some stainless steel plate fin heat exchangers that could be of interest for the low temperature seawater application. And they have also worked on the aluminum glued plate fin heat exchanger that could be also interesting for the seawater side. So as a conclusion, heat exchanger is certainly one key area and maybe the major key area in this development. For people, for risers, I would say for the above the sea, it's a key area. Certainly today for 5 and 10 megawatts, technologies are already existing without too many or too changes. But for 100 megawatts, there will be a need for new technologies to be developed. And this is an area on which we are working and following through partnership, alliances, and close relationship with manufacturers. Thank you.
Thank you for giving us this, merci beaucoup, I would say. Thank you for giving us this very good presentation on this critical component of any OTEC plant. Are there questions from the audience, please? No, you can keep it.
Well, thank you for a very interesting presentation. My name is Petter Destna. I'm the founder of an organization called OTEC Africa, and I also work at the University of Provost in Sweden. I have a poster in there. Anyway, I wonder, have you been considering using graphene coating for heat exchangers?
Graphene coating is something we are looking at, and the point is, as maybe we are a little bit a conservative industry. I'm coming from oil and gas, and so we need to have a demonstration of the duration mainly. The efficiency of the coating itself, I don't ask too many questions. The point is I need to deliver something that in 20 years we still be at the same level of quality and of operation. So this is this that I need to have the proof of this duration for this type. But this is clearly, yes, something we are looking at.
Okay, thank you.
Okay. Yes, please.
Thank you for exciting presentation. So, as you said, heat exchange is a very important technology for the OTEC. So, heat transfer coefficient is very important, but head loss is very important to get the net power. So, than another power plant. So, how you designed the maximum head loss of the heat exchanger?
In fact, head loss are clearly taken into account in the picture. This the comparison was made with the same head loss, allowable head loss for all technologies. So we are comparing the same net power, the same head loss. In fact, at the end, maybe we are not using all the same head loss each time because you don't have the same technologies, but the maximum allowable one is the same definitely for all. Yeah.
Thank you.
Thank you, Jeremy. Has Technip come up with design or capital cost estimation, say for 5 megawatt offshore OTEC?
Yes, my colleague, you know Jim, certainly Jim O'Sullivan that was there. Yes, they have performed this capital cost estimation regarding this 5 megawatt possibility. That's all. Sorry?
What's the figure?
I cannot share this. Okay. If you want, call Jim and he can share that, but yeah.
Yes?
René Lindeboom from Marin. I was wondering, what's the design life of a typical heat exchanger?
In oil and gas, this is something that we succeed to bring to 20 years for shell and tubes, typically. For plate and frame, you need to think about gasket replacement at a regular time, but it is something integrated in the procurement of the equipment. So you can have your plate going up to 20 years with a typical normal replacement of the gaskets, for example. Yeah. But this is, for us, mandatory. Starting from the first day of the project, we need to deliver something that will be operated for 20, 25 years with a very limited interruption. Mm-hmm.
Okay.
I am Kim from Korea. I have a short question.
Yeah.
And to apply heat exchange for ocean submarine composite system, anti-corrosion function is essential to resist seawater. So in your presentation, we have introduced stainless and aluminum for heat exchange material. Is there any way to prolong the anti-corrosion function of stainless or aluminum?
My colleagues studied some treatment, clearly some treatment of the seawater. This is one key issue. And what we face on offshore project is to have an end user managing in time a good quality of the treatment and to ensure a limited corrosion development. So yes, there are some technologies. After, it's to be sure that they will be applied without change during the 20 years. This is the main topic. So yes, there are some technologies, but I think the most important thing is to keep this applied all along. We know some projects for which at the beginning it was very good, and at one time there was some discussion about improving the cost, OPEX cost, and so they reduce or change the corrosion protection. And at the end, you have some big problems in the equipment, exchangers, towers, or whatever, because they change the corrosion protection. Yeah.
Final question there.
Yes, thank you. Matthijs Rabai from Laval. Thank you for the interesting presentation. I wonder, how do you see Technip's role in further development of this technology?
You mean for OTEC development?
Yes.
Yeah, this is today technology that we are working on and following to see what is clearly happening. And after, I cannot answer at the place of my bosses, clearly. But we are following. We know that, for example, our main end users, such as Total or Shell, are also moving, and you mentioned COP21 last year, and this is clearly a statement from Total and Shell to go in this direction. And so this is a topic that we are looking at clearly, yes.
But is it more like an EPC role or more like a technology development role?
Very good question. If you talk to me, I would be technology development. Clearly, this is a very interesting thing for me, not only to do engineering and installation, but technology. And I think Technip, this is something that is quite open. On the second or third slide, regarding R&D, I presented 2 topics we developed, 2 projects, DSTA and GEWA PB tubes. This clearly is technology, and it is for onshore and offshore application. So, yes. If I'm only the decider, I go for technology.
Thank you.
Okay. Thank you once more for this very interesting presentation.